no go fit in my shoes. High fashion, Jimmy choose. Wanna sip something and choose tomorrow. Espiritu Fortuna, I go make you Joe Dada. Say you get the power. Sweetie Passy, Amala Ketu. Shinji Bagawa, Jesu Christi Lobawa. But them falling Yakata. You know what Sabi girl they do.
But this year I want a billion more. I'm not feeling like I need me or what. Make it come and reach activity on top. Sorry, they call and they busy of course. It's been a roller coaster riding in my head. One more round, see evidence is all around. Suffering and smiling, you're around. No grief for person, come around. All that I am, intelligence is number one. Something that stress you, cut them out. Too much plenty on them out.
And I mind my business. God is my witness. They don't see my vision. I'm a local journey, moonlow. 1 in a million. Waiting them talk, say I do now. Yawade, yawade, yawade. Otojimola sọ̀rọ̀ mi, jẹ́ kó máa sọ̀rọ̀ no. Yawade, yawade, yawade. Otojimola sọ̀rọ̀ mi, jẹ́ kó máa Jelly go my way, but them say, kilo one day, get it too fat, get it more shit. I did jelly go my way, anything I do, them say, Yawade, Otojimola sọ̀rọ̀ mi, jẹ́ kó máa sọ̀rọ̀ Yawade, Otojimola sọ̀rọ̀ mi, jẹ́ kó máa solo, I be sure boy, I no thief person, no. Enter my convoy, we dey burn up, I don't dey smoke it, go. One back to the roll up, put the jog up, I don't see person, no. Don't give a fuck, anything you talk, I did more than enough, I've been on the block, I've been giving it all on the dance floor, 24/7, 1 o'clock, and I swear to God, I want me one coming go 365 days, we dey burn it up. Life on the road, always on the go, we dey throw the rig in my road.
Hello. A very good afternoon to you all. You are all warmly welcome to the AIMS Ghana QTEdu public lecture. We want to first of all acknowledge your presence with us here. According to our program, the hours of between 2 and 3 was for networking and getting to know each other. But as usual, when we go to events, most of us like to stay back relax in your seat and not engage the people around you. But we understand there'll be another session for networking after the main event has ended. But it will be nice to extend a warm welcome to the person seated next to you. So if you don't mind, kindly say hello or hi to the person seated close to you. Remember, we are going into the future today. So you need to be sure of your surroundings so that when you get into the future, by the power of quantum technology and science, you will appreciate the power of the future. So once again, you are all warmly welcome. We are very happy to have you all here. We are starting our program, and I can assure you that you will have a lot of fun, you will learn a lot of things, and most importantly, you will leave this place with a renewed mindset about the power of quantum technology and science. So ladies and gentlemen, brace yourself, put on your seatbelt, and be ready for the journey into the future. If you are ready, let's have a big round of applause for ourselves. To officially welcome us, we are very privileged to have with us the president of the African Institute for Mathematical Sciences, Ghana. He happens to also be the director for Quantum Leap Africa. And this is our event, and it is therefore necessary that we have the head of our institution come to welcome all of you. So ladies and gentlemen, can you put your hands together? Let's welcome Dr. Prince K. Osei to do the welcome address.
Thank you very much. It's been an exciting week throughout all the events that we've been running under the quantum technology education. I want to especially welcome all of you, those of us in the auditorium and those who are watching online. I want to welcome you to this conversation on quantum science and technology. The impact of quantum technology will be far-reaching, potentially offering opportunities across multiple disciplines, leading to advances in sectors such as healthcare, climate change, communications, finance, and others. Quantum physics allows a deeper understanding of our natural world, and it is now able to make it possible for us to harness the principles of quantum physics to develop technologies that are more powerful in areas like quantum sensing, quantum communication, and quantum networking. Today, we are here to listen to a lecture and other conversations on quantum science and technology to become aware of the impact of these emerging technologies. The motivation for this lecture is the fact that this year marks 100 years since the discovery of quantum theory. And the UN has declared the year 2025 as the International Year of Quantum Science and Technology. And this was heavily led by Ghana, and Ghana played a very crucial role in making this declaration happen. I want to welcome you all to this event and fasten your seatbelts, and I want to encourage you to open your minds to understand the conversations. And for the young ones who are here, I want you to get inspired to pursue careers in quantum science and technology. At AIMS, we believe that the future of science belongs to the young people of Africa, and we want to provide opportunity for young people to lead discoveries and innovation in these emerging technologies. So thank you once again, and welcome to the program. Thank you.
A bigger round of applause for Dr. Prince Osei, who is the Center President for AIMS Ghana and also the director for Quantum Leap Africa. And it's good to know that AIMS is not in this business alone. We have a lot of very significant partners globally and locally who are helping us to push the agenda of empowering young Africans with science, technology, and maths. And I'm very honored again to invite upstage one of the very influential people in the STEM cycles, not only in Ghana, but across the world as well. And the University of Ghana happens to be a partner to AIMS, one of our partner institutions we work with. And today we have in our midst a very popular name. When I mention, I'm sure you all start clapping. We're happy to have Professor Elsie Efa Kaufman, the Dean of the School of Engineering, University of Ghana, and a very strong partner to the AIMS agenda. Ladies and gentlemen, please put your hands together for Professor Elsie Efa Kaufman. This is the closest I'll get to science and maths quiz, so yes, I'm very happy.
Center President, distinguished lecturers and panelists, invited guests, ladies and gentlemen, good afternoon to you all. Oh, good afternoon. It's a pleasure to be here this afternoon participating in the celebration of the International Year of Quantum Science and Technology. I bring you warm greetings from the School of Engineering Sciences here at the University of Ghana. You are all very welcome. At the School of Engineering Sciences, we are training the next generation of problem solvers. We like to think that our students are open-minded and they are ready to learn. And so an event like this is very close to us, and we are happy to have been invited to participate in it. Thank you very much, AIMS. Thank you so much. Now, we are looking forward very much to what is about to unfold here. It's another learning opportunity, another opportunity to look into the future to see what is coming. Students, I hope you are also anticipating this as much as I am. Yes. So we are looking forward to it, and I don't want to spend any more time talking. We want to get right to it. But I'd like to extend a warm welcome to our visitors who are here for the first time on our campus. We invite you to make some time to look around. You'll be amazed at what you see here. So on this note, thank you so very much. We look forward to more interactions with AIMS and more interactions with our guests who are here, so that we learn more and we have more to share together for the rest of the International Year of Quantum Science and Technology. Thank you very much.
Let's put our hands together again for Professor Elsie Kaufman. Thank you very much. Thank you once again. Ladies and gentlemen, it is time for us to take our keynote address. And like I indicated, AIMS Ghana has a lot of partners globally and locally. And we're very happy to have one of our key partners here in Ghana with us. Ladies and gentlemen, I want you to put your hands together as we welcome Stefan de Couturier, who's the Secretary General of JESDA, to come and give us his keynote address. Please put your hands together. Thank you very much.
So good afternoon, everybody. I'm very pleased to be here with you. And I've been here all the week, in fact, participating both in the Quantathon, in the education workshop, and today's in your public event. And as it was just said, I'm representing here the Board of Directors of the Geneva Science and Diplomacy Anticipator Foundation, in short, JESDA. And I must say, JESDA which is a young foundation, only 5 years old, is very proud to be an official partner of AIMS Ghana into this endeavor, and this very successful endeavor. What I would like to do in the few minutes that are given to me is to share with you two things. The first one is just to tell you a bit more what we are doing and why you are here, and why it could be of interest for you to liaise with us also. And the second thing, more importantly, I would like to exchange with you a few lessons I learned by being with you, being in Ghana this week with AIMS. So I'm starting with some comments on what GESDA is doing. Our task as a foundation, as a private foundation in Switzerland, is to develop an instrument of anticipation and action that allows scientists, politicians, diplomats, entrepreneurs, philanthropists, and citizens of the world to benefit as early as possible from emerging science disruptions. One of them is a mix between artificial intelligence and quantum computing, for instance. But there are many others. So there are many opportunities for you if you take courses and you go all the steps in order to go into markets, economy, and if, for instance, you build your own company. Why does this matter? Why is it important to develop, to be anticipatory and to be active? It's very easy because we are all living in a world accelerated by science and technology, but of course not everybody benefits quickly enough of these advances, nor participates enough in their development. And this is not sustainable, and that's why we think that the path to sustainability is to democratize as much as we can both the early understanding and the early uses of emerging science breakthroughs well beyond the initial developers of these breakthroughs. And that's what we are doing. We try to develop tools at GESDA that first promote science literacy. And we do this, for instance, by editing every year with 2,000 scientists from all over the world, of course, including Africa, what we call a GESDA Science Breakthrough Radar. We gives you a glimpse, as seen by the scientists from all over the world, what is cooking in the labs and what will emerge or could emerge from the labs at 5, 10, 25 years. It's not always an exercise that the scientists like to do themselves. At 5 years it goes well, and after they might be from time to time a bit reluctant. But if you do this every year, then you can follow up on what is changing and what is accelerating, for instance, generative AI or some other fields, and what is also a bit more on the brakes. This is for the promote science literacy, but it's not enough to promote literacy. What is the real thing? And I know I am speaking in front of the chairman of Ghana.com Ltd, Mr. Quaynor, and we need to go to also to speed up the uses, even of early emerging technologies, to get, if we don't apply this at once, you will be prepared the day this technology really thrive. And this is the only way we think to have a chance to go into, to take benefit of these breakthroughs. And that's why we launch what we call the Quantum for All initiative. One is the Open Quantum Institute, which is located in Geneva but is working worldwide. And we also launch a contest with some partners from Google and some partners in the US, the X Prize Foundation, with the goal to accelerate the development of use cases in the most promising fields of quantum computing, for instance, water sanitation, food water materials for carbon capture, and so on. And just a figure, so far 240 teams have applied to participate in this contest, and from 39 countries, of which 4 are coming from Africa. And I just quote them: Nigeria, Morocco, Egypt, and of course, Ghana. Now, what we are, so what I want to say with these examples is even we are located in Geneva, Switzerland, which by the way is the second hub of the UN nations also, we want to be a global initiative because knowledge should not have any border, or at least not too many borders, and because we are all equals in face of knowledge. We have the same brain capabilities whether we live in a country or another one. That's why we believe, and we are very present already in Africa, and that's why I must say that it's not a coincidence if we are here during this week. If I am here during this week, I am also with my colleague, Philippe Kammerlander from the Open Quantum Institute, but because we truly believe in what you are doing. Especially, I mean here, the people who participated, the 6 teams who participated in the Quantathon this week. And we truly believe in this, and you may say us as a sustainable investor and partner, should you wish to. And what I would like to insist in my conclusion is to say that not only that how much I found impressive the work made by AIMS and the people participating in the Quantathon, but because it rings a bell by myself. I'm a strong believer that what you are achieving demonstrates the possibility for AIMS and for all the people and countries in Africa to leapfrog several important steps on your own way to excellence, innovation, and growth. And that's, I can only but encourage you to get interested in AIMS activities or in other university activities, the Center for Excellence in Africa and so on, because this is really the future. And I would conclude by saying that if I don't want to give any advice, but just to have a dream for you and for us, because I think we are all on the same world, and we need to be connected, to keep connecting on because we will be better all together because there is a lack of talents worldwide. And of course, you are part of the solution altogether who are sitting with us today. I would like to emphasize 3 elements that I learned from this week. First, anticipation, preparedness matters on the very cutting-edge breakthroughs that are upcoming, for instance, quantum computing. It's worth working early on those topics, such as quantum computing. The second point is think the end. So it's not about knowledge only. It's about jobs, market, products, innovation. And so to do this, you need to think the end goal of what you will be doing, for instance, thanks to an algorithm, in a quantum algorithm. This is I can only encourage you to do this. And to do this is my 3rd point, use cases. I was very impressed, I must say, Prince, yesterday. If I see the teams who won, one is on malaria, one is on energy, on desalination of water, the 3rd one on energy stability, the 4th one on traffic optimization. These are very concrete things. And for this, maybe, and hopefully, you can go the last mile, and the last mile having a solution, which is a product, which is embedded in a company, and which creates jobs. And jobs, of course, I mean here, and not only. It can be that there is something that is also made in other parts of the world, but there must be something anchored here for you, and thanks to you. So without making too many symbolic quotes, but this night I made a dream. And the dream is the following, Prince, that We have been organizing Quantathon. We'll be organizing, the Open Quantum Institute will be organizing a Quantathon also where the winning team will participate, if I'm not mistaken, in October. We were part of a Quantathon 2 years ago in Abu Dhabi, and there will be also a new one. What if, this is my dream, what if you were able to gather the different winners of these Quantathons and to go with them, of a few of them, the next steps, so they can pitch one day their projects when they will be a bit riper. They can pitch it to real VC investors and go to market here. So this is my dream, and I hope you fulfill it. Thank you.
Let's put hands together for Stefan. That was a very powerful speech. If there's one thing you need to go into the future, it is your dream. Can I see by show of hands people who have dreams and aspirations? Yes. To us, that dream, everything is possible. Thank you, Stefan. Please put your hands together for him once again. I'm also very happy to introduce another speaker onto the stage, Professor Ni Nakukweno. He is widely known as the father. Oh, you wait until I finish, please. Good. It means he's a very powerful, popular person here in Ghana and across the continent. He is widely known as the father of the internet in Africa. And he's a Ghanaian computer scientist who has played a very pivotal role in establishing internet infrastructure and promoting the development of the internet across the continent. He is also the first African to be selected or elected to the board of the Internet Corporation for Aligned Names and Numbers, ICANN. And ICANN oversees policies and protocols related to internet domains and addresses. And he has served as a director at ICANN for the African region from 2000 to 2003. Ladies and gentlemen, such a legend is in our midst today. Please put your hands together. Let's welcome Prof. Kweno to the stage.
Well, thank you very much for the kind introduction. Ladies and gentlemen, it's a pleasure to participate in the Quantum Technology Education Global Event and to speak at the public lecture, Our Quantum Future. The overall theme, Accelerating Capacity Building to Advance Quantum Science and Technology, is very well aligned with my lifelong efforts in building technical capacity in computing sciences. As these are Professor F.K. Alote public lectures, celebrating International Year of Quantum, I thought I might share a bit of history in computing in Ghana, in which Professor Alote played a pivotal role in my opinion. This is a story I've always wanted to tell, but never quite had the right public forum, but I think this forum is most appropriate. And I'll tell the story in 6 episodes. Thereafter, I'll point to some interests in quantum computing and communication. We are going to talk about computing with my father, where Professor Alote is my intellectual father. The background is this. I arrived in the US in 1969 to study in a small Ivy League school called Dartmouth College in New Hampshire. Not aware the school had reputation for computing, boasting of having coined the description AI, artificial intelligence, pioneering a computer time-sharing operating system, Dartmouth Time-Sharing System, DTSS, creating programming language BASIC with a student workforce assisting at Kiewit Computer Center, where dormitories had terminals connected to the Dartmouth time-sharing system for computing access, meaning campus network. Well, armed with a strong physical sciences, I studied engineering science program and joined the Dartmouth time-sharing student workforce during my undergraduate studies. Episode 1. Professor Alote was in 1972 beginning to establish a computer science department at KNUST, offering data processing courses. He was in need of PhDs to come back to lead the burgeoning department, and from his intelligence, he knew I was graduating. I had not met Professor Alote, but in his own words, he talent searched and communicated with a Jeffrey Rothmeyer of biomedical computing at the school, where I was implementing a project interconnecting a mini computer monitoring heart patients with heart waves to this sprawling campus network they call Dartmouth time-sharing system. Prof sought funding for my graduate studies at State University of New York, Stony Brook, to secure the first known PhD in computer science in the sub-region, as he stated at an Ames event in Labadi Hotel. The research area was distributed systems, graduating in 1977. My father had intentionally produced the first computer scientist, rare at the time, which he needed and would benefit Ghana and Africa. Episode 2. A true father indeed. When I returned to Ghana in 1979, I was to join KNUST and all arrangements had been made. Yet, he asked me to go evaluate the programs on quantitative sciences at University of Ghana and University of Cape Coast, after which we chose to kickstart computer science department at University of Cape Coast. That is how the computer science department was seeded at UCC. Episode 3. Now, the father challenged the son to answer a very basic question. How did our forefathers, Africans, compute? This resulted in a paper presented at a Boucher conference showing that the native Owari board is a Turing-complete mechanical computational instrument with very simple operations on the board. I had to show it could do sequencing, it could handle conditionals, it could do iteration, and it could store on the board. This came along, of course, with algorithms for the simulator itself and AI for the games in Ghana, meaning Nanti Nanti, Abapa, and so on. Boucher was the first African physicist PhD, Yale, 1876. That was not accepted by the environment then, and he could not reach his real potential in USA. So my father used to say to me, in quotes, do not become the Boucher of computer science. I dare say to you, do not become the Boucher of quantum computing. You can see videos on this thing at my YouTube channel. Episode 4. In the late 80s, while an instructor at microprocessor colleges of International Center for Theoretical Physics, ICTP in Trieste, many scientists from here go there, we're training scientists on interfacing microprocessors to their lab experiments, experimental equipment. The Ghana Atomic Energy Agency hosted one of the workshops in Ghana. The chairman of GAIC was Professor Lotte. And we went on to advocate to address the very large-scale integrated circuits divide, VLSI divide, an earlier digital divide about access to chips. Is still a big problem now, scientists' access to chips. Episode 5. In 1993, the talent search and investment in computer science paid off, and the distributed systems expertise invested in the 70s yielded one of the first internet connections in West Africa. Prof was also one of the first subscribers, and his handle was fka@ghana.com, which he used until NCS was shut down in 2003. Episode 6. We have gone into communication, and when solar eclipse passed Ghana in 2006, Prof tasked me to telescopically, digitally capture the passage and transmit it live to all scientists around the world, as well as display it live at the University of Cape Coast Auditorium for science education purposes. With very limited resources, we configured a distributed network, quite ingenious, of 3 centers, one at UCC Observatory as the source. We only sent information out. Okay. And of course, we networked, pushed it to the auditorium. And then we had relays in South Africa and North Carolina. So they took all the hits. We didn't have bandwidth. So we pushed good stream out to 2 different countries, hedging on resilience, and then we took the hits from there. So when you don't have, you are forced to think deeply about solutions to problems. We knew from forecasts that we could not bring the user traffic to Ghana. I mean, it's just impossible. So we used 128 kilobits. We split it 64 to North Carolina, US, 64 to South Africa. But we relayed excess of 35 megabits per second user traffic. Okay, 100 years of research is giving quantum physics a real life. We expect quantum computers, quantum networks, quantum cryptography, quantum everything. From bit to qubit, we will learn and use new methods of calculations and processing. Computer scientists who analyze algorithms live by complexity in the theory of computation. We accept different classes of problems, fast, slow, others impossible, such as halting problem. We welcome quantum algorithms that promise computational complexity capabilities beyond classical algorithms. Algorithms that factor large numbers rapidly, perhaps at log n complexity, big O of log n to some power, like Shaw, or algorithms for unstructured searches, improvement from order of n, big O of n, to even square root of n, as in Grover, and several others, will enable many new opportunities of faster solutions, as well as new, stronger cryptography, but threatens existing cryptographic algorithms. While the world is preparing to enter quantum life, it is also actively preparing to migrate many quantum vulnerable systems, so to a post-quantum world is on the way. Although there's quantum computing divide, equipment are not yet commercially available, and there's opportunity to engage and be part to prevent the divide from widening. Perhaps even in Ghana here, unrelentlessly, we should ask for our quantum part of the 1 million coders in our part of the world. In conclusion, it is when one is constrained, when we are constrained, that we bear down and think and build. With my father, We went from computational physics, computer science, internet, AI, blockchain, and we are on to new quantum computing worlds. We admittedly are in a quantum divide. However, it is when you are constrained that we think deeply how we can be part and engage. Please, just don't become the boucher of quantum computing. Make it work and make it have impact. I thank you very much for your attention.
Thank you so much, Prof. Queno. Very inspiring. And we need to understand that we cannot go into the future without the past. And it's important that the young people who are in the present take advantage of the past, prepare yourself now, and let's go into the future together. A big round of applause for Prof. Queno. Thank you so much. So for those who missed out the action, I would just like to recap what has been happening over the past few days. So the aims, as we have it there, Quantum Technology and Education Global Event, featured three main things. And most of the speakers that have come here, they have mentioned the hackathon and Quantathon. But the Quantathon was part of the whole lineup of events for this celebration. So we have students from across Africa gathering here in Ghana, AIMS Ghana, to brainstorm and come up with solutions, applying quantum technology and science to develop these solutions. Yesterday was the climax of the Quantathon, and I think the winners for the event are here. Can we see the winners? Can you see, show by hands? Please be on your feet. Let's clap for them. So out of the 6 teams that competed, these are the winners that emerged from that very rigorous and engaging activity. Thank you very much. Thank you. Please have your seats. And then also there were a series of workshops that were conducted under the auspices of AIMS and Google. And we had experts from across the world coming together to look at how we can develop a blueprint with which especially the young ones can learn about quantum technology and be actively engaged and a part of the entire process. And today happens to be the climax of all these activities that went on over the past few days, our public lecture. Now, to introduce our main speaker for the public lecture, I would want to introduce to you one of our own. When I say that, I mean she's been a product of AIMS. She had a master's degree from AIMS. She went on to tutor or serve as a tutor in AIMS, and now she's pursuing a PhD. Ladies and gentlemen, please put your hands together. Let's welcome Jennifer Ahiable as she introduces to us our main speaker for today. A big round of applause for her.
Good evening, and a very warm welcome. The topic of our lecture today, our quantum future, pushes at the very boundaries of our reality. To explore it, we are incredibly honored to host a physicist who is not simply contributing to our understanding of the quantum world, but is one of the visionary minds actively shaping its future. It is my profound honor to introduce Professor Jonathan Oppenheim. Jonathan Oppenheim is a professor of quantum theory in the Department of Physics and Astronomy, specifically in Quantum Information Group at University College London. He currently holds a Royal Society Wolfson Merit Award and an EPSRC established career fellowship. He completed his PhD under Bill Unruh at the University of British Columbia in 2001 and was a postdoc under Don Page at the University of Alberta and Jacob Bekenstein at the Hebrew University of Jerusalem. In 2003, he moved to the University of Cambridge, where he held a Royal Society University Research Fellow. In 2012, he moved to UCL to take up his current position. Professor Oppenheim's recent research is focused on the field of quantum thermodynamics, which has recently seen exciting progress inspired by ideas from quantum information theory. He is also active in the fields of quantum gravity, black hole thermodynamics, and the foundations of statistical mechanics. Although these fields are often distinct, there are many conceptual overlaps. His contributions include the discovery of new second laws of thermodynamics that become important at the quantum scale, and the discovery of negative information and quantum state merging. He is currently applying results from quantum information theory to understand black hole thermodynamics and quantum gravity. He is particularly interested in the black hole information paradox and holographic entanglement, an attempt to understand gravity from a thermodynamical perspective. Ladies and gentlemen, please welcome Professor Jonathan Oppenheim.
Can everyone hear me? Okay, great. So thanks very much to Prince for inviting me, and to Prince and the organizers of this event and such an incredible week of quantum hacking. I've been very inspired by AIMS itself as an institution and by the researchers and students who I've met. Now I'm going to tell you two quantum facts. I will share with you two quantum puzzles and discuss two quantum applications. And there will be a quiz afterwards, so maybe stay off your phones. There will be a couple times during this talk where many of you will become confused, and I think the main thing about being a physicist is that you should try and enjoy that confusion. We have to enjoy that confusion because most of the time we are confused ourselves, and I think the key part is to not really, to enjoy it, to kind of lean into it a bit, to try and think of what questions you could ask in order to get around that confusion, and maybe just to think about it a bit after, and ask questions when you have an opportunity. The other thing that I think physicists need in order to become good physicists is not so much intelligence, but I think curiosity. So this is Pauli and Bohr, two of the founders of quantum mechanics. You can see they're very curious. They're probably also confused. And I imagine since you're here, you are also curious, unless your teachers made you come here. Okay, so let's talk about quantum mechanics. And quantum mechanics is, it's the theory of the very small. So in physics, size matters a lot. We have very different laws of physics depending on the scale or the size that we look at things. So the world that, when we think of someone our size, we call this the classical world, the laws of physics that kind of correspond to things that are our size. If we look, say, 1 billion times larger than us, we get to something which is around the size of the sun. And that's where the laws of gravity become incredibly important. And gravity is considered one of the pillars of modern physics. But quantum mechanics is maybe 10 billion times smaller than we are. So when we look at, say, we want to look at, say, our finger, which is smaller than us, and our finger is made up of molecules like water, and those molecules are made of atoms, and those atoms are about 1 billion times smaller than we are. But our hand and the atoms in our hand is almost all nothing. Okay, like a molecule of water or an atom in that molecule is 99.9999 with 13 nines. It's 99.99999% nothing. And the laws of quantum mechanics, they hold in that atom, which is almost all nothing and just contains tiny, tiny particles. So that's the scale where the laws of quantum mechanics really matter. And the laws of quantum mechanics are so incredibly weird and unfamiliar to us because we are so much bigger than the atoms and the electrons in our hand. Okay? I should have asked to find out what people's confused look looks like and what people's not confused look like. So I have can people give me maybe their confused look so I know when they look confused and what their not confused look is like? It's exactly the same. Okay. Yeah, now I'm confused. Feel free to give me some feedback. If you're confused, you can kind of look like this, and if you understand, you can nod, and then I'll slow down or speed up. Okay, so the laws of quantum mechanics is the laws of the very small, and as physicists, we try and imagine what it's like to be very small. And the way that I like to imagine being very small this is called the Sloan Digital Survey, and I watched this. These are actual galaxies. Each blur is a galaxy, like our Milky Way. So our Milky Way is one of these little blurs. This is not a fake AI video. This is actual galaxies. And when we look at the stars around us, we are only seeing one galaxy. So this gives you a sense of how large the universe is and the large scale it is. And I can use this sometimes if I want to feel small. So once we feel small, we can try and understand what the physics of the small is like and what happens to very small particles and how are the laws of physics different for very small particles. So I said I would give you 2 facts about this. So here is almost one of them. I am here and you are there. Particles can be in a sense, they can be both here and there at the same time. And they can be in some sense, in many locations at the same time. It's also the case that they can be neither here nor there at the same time. And so what we do is we say that particles are in a superposition, it's a technical word, a superposition of being in many places. So a particle can be like an atom or an electron, can be in a superposition of being here and there at the same time. So particles, very small particles, they behave like waves in some ways, that they're spread out throughout space. Whoop. And we only find out whether they're here or there when we look at them or observe them. Are people confused or not confused? Not confused. This is related to a key part of quantum mechanics called Heisenberg's uncertainty principle. And in its first version, it means that if we know the speed of a particle, then we don't know its position. We don't know if it's here or there or where it is. And likewise, if we know the particle's position, then we don't really know the speed. Now, when this was first proposed, people like Einstein were very much against it. Einstein, for example, refused to believe that a particle didn't have a position. He thought somehow particles do have positions, we just don't know what they are. And he somehow refused to believe that the particle would, when we looked at it, would just randomly be in some position. He famously said that the old man does not play dice. So this debate about quantum mechanics, whether particles have definite positions or not, this went back and forth for quite some time. And this man, John Stuart Bell, in the 60s, I think, made one of the deepest discoveries in physics. So if I have to tell people what is the most profound thing that physicists have discovered, I would say it's John Bell's discovery, which is sometimes called Bell's theorem, if you ever want to search for it or discuss it. So John Bell proved something called Bell's theorem. And what he showed is that in quantum mechanics, it's not just that we don't know where the particle is, it's that the particle doesn't have a position. Okay? So if we think of Heisenberg's uncertainty principle, which if you were taught it ever, it was that we cannot know what the particle's position is if we know its speed. It's actually a lot deeper than that and a lot more weirder than that. It's that if you know a particle's speed, if we know the speed at which an electron is moving, then it actually doesn't even have a position. It's not just that we don't know the particle's position if we know its speed. It's that the particle itself doesn't have a position. That's not, we would say, that doesn't have there's no element of reality, of objective reality, that corresponds to the particle's position. And in the 70s and 80s, people actually experimentally showed that it's true, that the nature around us obeys the laws of quantum mechanics in a way which demonstrates that the particle doesn't have a position. So this is an experimental verification of that quantum mechanics, we say that it violates Bell's theorem. It's not a locally realistic theory. Quantum mechanics has the property that particles have definite positions. And this was demonstrated experimentally in the 70s and 80s and has won a Nobel Prize many years later in 2022? Yeah, in 2022. So many years later, people finally gave Clauser, Aspect, and Zeilinger the Nobel Prize. It was 40 years after they'd made this discovery, I think because no one believed it, because it's kind of mind-blowing that the things we consider as objective elements of reality, where something is, in the quantum world, that does not exist. The quantum particles do not actually have positions until we measure it. So I promised you 2 facts about quantum mechanics, and here they are. I'm just summarizing them. So I think these are the 2 most important facts about quantum mechanics, if you had to distill them into 2 little facts. And the first one is that quantum mechanics is indefinite. Particles do not have definite positions. There's no objective reality to where the particle is until we measure it. And then the second thing is this notion that we measure the particle to find out where it is, and only then does the particle have a position, and that happens with some probability. Where it is turns out to be some random probability, as if someone threw dice, and this only happens when we observe the particle. Can people give me their confused face or their not confused face? Same face. Okay, so those are the 2 facts I promised about quantum mechanics. And now I'm going to give you 2 puzzles, because I think that's sometimes the most interesting part about physics. It's the things we don't understand. So I'm going to give you the 2 things we don't understand. And the first thing, actually, you can see I put that I put the word observed in quotes. I said, we don't know where the particle is until we observe it. What does that mean? Is it that I should observe it? You should observe it, your friend should observe it, a robot should observe it? Is it just enough that the molecules in my eye observe it? What about the molecules of air? Can they observe something and make the particle have a definite position? We kind of believe that all those things act in some way as an observation and cause a particle to have a definite position, but we don't understand many aspects of that. So particles can be in a superposition of being here and there at the same time, but we don't see that sort of behavior on our scale. We only see that observed for very small things. So we don't see big things in superpositions of being here plus there. Likewise, Schrödinger kind of summed this up by saying that you could imagine a cat which is in a superposition of being dead or alive at the same time, and we do not see cats which are dead or alive at the same time. Why is that? This problem is known as it's like a Schrödinger's cat problem. So here you have a cat who's in a superposition of being both dead and alive at the same time. And it has to choose one of those things. If we look at it, it'll collapse into being either dead or alive when we open the box. Fortunately, in this case, we find it's alive. I didn't want to kill a cat in front of a large audience. But it's a mystery as to what determines whether the cat is alive or dead. Is it just randomness? Is it just some apparent randomness? This is all the mystery. The other mystery we have is that we believe that all the matter in the universe obeys the laws of quantum mechanics. All the forces of nature obey the laws of quantum mechanics, except we're not sure about one of them, which is gravity. So gravity is Einstein's theory of general relativity, which holds that large objects cause the fabric of space and time to bend. And we have a theory of quantum mechanics. There's Schrödinger, one of the founders of quantum mechanics, Einstein, the founder of general relativity. These are the two pillars of modern physics, but they're not compatible, because if a particle can be here or there, well, we haven't found a way to make space-time be in a superposition of two places at once. We don't even really know what it means for space-time to be in a superposition. So those are the two puzzles that we still don't understand and which physicists are still struggling with. I will now tell you the two applications of quantum mechanics. And for a lot of the history of quantum mechanics, physicists argued back and forth about whether, how could quantum mechanics be so weird? How should we interpret all these strange behaviors? And eventually, in the late 80s and 90s, maybe they got sick of arguing about why quantum mechanics was weird, and they were just thinking, okay, quantum mechanics is weird. Can we harness that weirdness for something? And so I'm going to be telling you two ways in which we harness that weirdness for some applications. And the two applications I'll mention are quantum computers and something called quantum sensing, which is like precision measuring. So that's a classical computer. And maybe you know that we can encode any question we might have as a string, as a sequence of ones and zeros. These are called binary strings. So it's a bunch of ones and zeros is called a binary string. Let's just call it a string of ones and zeros. You can think of this string of ones and zeros as being like a sentence or many sentences, and we can encode, it's like a language, and we can encode any question we might have, any mathematical problem. We can encode it as a sequence of ones and zeros. And so what a classical computer does is it takes the input of a bunch of ones and zeros, and it does a bunch of manipulations of those ones and zeros, and then out pops an answer. But sometimes that answer takes a very long time, and we would like to sometimes get an answer quicker because we are very impatient. And there are lots of questions we care about where we might be able to know the answer quicker. So along comes this thing, this quantum computer. And if you remember, I said that quantum mechanics, one of the key facts about them is that a quantum system can be in a superposition of many positions. And so what quantum computers use is, instead of bits, they use something called quantum bits or qubits. And just like particles can be in a superposition of many places at the same time, a quantum bit can be in a superposition of many different values at the same time. So a quantum bit can be, a 0 and a 1, or a superposition of a 0 and a 1 at the same time. So here is a 3-bit string, a superposition of 3 different bit strings. And I have to be careful here, but essentially a big part of what a quantum computer is doing is that instead of feeding in a single bit string with a single value, you feed in quantum bits which are in a superposition of many different strings, and the computer does a parallel computation on each string. And then if we are very clever about choosing the computation that it's doing, and if we're able to combine all the parallel computations in a very clever way to arrive at some global mishmash of all those different computations, then we can perform a measurement and get the answer to the question we were actually interested in. And that's how a quantum computer harnesses the weirdness of quantum particles being in many places or being in many states at the same time. Now that's an amazing thing in terms of it will allow us to solve some important problems. So for example, if you want to simulate a material, well, materials are quantum. Everything is quantum, all matter is quantum. So if you want to simulate a material to find out what it does, then it is often much quicker to do on a quantum computer. Likewise, drugs, and when they interact, say, with a virus, then that interaction often requires some quantum understanding of the molecular structure. And maybe we can simulate that on a quantum computer. But the quantum computer it's going to be in the superposition of many different, the bits having many different values. And to me, the remarkable thing is not just that it's a useful thing to do, it's that we are going to create this thing in a lab which is very much like a cat which is dead and alive at the same time. So all these little particles, they obey the laws of quantum mechanics. And now what we're doing with a quantum computer is putting them all together. And so the whole quantum computer contains a part of it which is like a cat in this a large system which is going to be in a superposition of many different states at the same time. And conceptually, that's kind of astounding, because what we're doing is we're dragging the quantum world up into our own domain. It's going to become almost the size that we are in some sense. So when I showed you before this picture of us in comparison to the atoms which make up our body and which obeys the laws of quantum mechanics, if we are successful in building a quantum computer, we'll create something of our size which is obeying the laws of quantum mechanics. And that's, for me, an amazing thing, but also shows how difficult it's going to be. And we anticipate, well, depending on who you talk to, decades probably. It's one of the great challenges of our time. The second thing I want to tell you about is quantum sensors. So that's another application of quantum mechanics. So we can use atoms which are in superpositions of many places at once. We can use designed diamonds that can be in superposition states. And we can use these to perform all kinds of precision measurements. We'll be able to image materials that we couldn't image before. At my university, we're using quantum sensors to test whether the fabric of space and time is quantum or not. They can be used to detect the minutest level of viruses, probably in handheld devices, which is very useful in a country like Ghana. And so those are two of the applications of quantum mechanics. So let me close. I think the thing I like about quantum mechanics is it really changes how we see the world, and quantum technologies help us change the world itself. How we do that is, we have a role and a hand in that, and I think I've been very inspired by the passion that the students I've seen here are bringing to the problems which are relevant to them, and so I feel very fortunate that this future is in your hands. So thank you very much for your attention.
That's the question.
Thank you very much. That was amazing. Shall we give a big hand again for Jonathan? So we have time for questions. So I have put him on the hot seat. And I know there are questions. I have 3 questions, but I want you to ask your questions before I ask mine. Can we have some microphones up there? Please raise your hand if you have a question.
So in your talk, you spoke about the 2 sizes, the size dimensions, like very small and the very big. And I know currently we have the standard model that's helping us with parts of the very small. And I want to ask, what are we currently doing to try and incorporate gravity into the standard model? And also, what potential benefits might that bring us in the future, if we're able to do that?
So maybe we can take 2 questions and then, or 3, so that, yes, it will be helpful to us. Yes, please. Please mention your name first and go ahead with the question.
Yes, thank you so much. Now, my name is Thomas Kanga. And with the current states of quantum, both globally and Africa's landscape of challenges, being internet, infrastructure, and other factors, how soon or what will be the application of quantum in solving our rare use cases, being in health, education, industries, and other domains? How can we utilize quantum in life application solutions in our current situation? And how do you intend to address those challenges? Thank you.
Okay, thank you. I will let Jonathan answer the first question. The second question will be mostly addressed by the panel, but you can comment on it.
So the question was about the standard model, and I sometimes like to not call quantum mechanics a theory as much as a framework. So we don't know, like, you can imagine how to put it, quantum mechanics works for, if we change the standard model, and we have different kinds of particles, different fields, different forces, we would still have quantum mechanics. So quantum mechanics sits below the standard model. It's so fundamental, it is almost like a recipe for how we do physics. Likewise, classical mechanics, well, there's all kinds of different forces that could be classical, or classical at the scale we're interested in. And classical mechanics is not we don't need to know what the forces are in order to have this framework called classical mechanics. So classical mechanics and quantum mechanics sit underneath everything. And we don't know of any others, and maybe there will be a new thing that comes up, but at the moment, these are the two kind of frameworks that we have. And then we fit them into then the standard model fits into the quantum framework, so depending on the kinds of fields and forces, we apply quantum mechanics to those. But you could imagine different universes, and maybe there are different universes, where there's different fields, different matter fields, different forces. And so at the moment, we're a little bit stuck in that we think well, maybe not stuck, but maybe we don't know, we think we've discovered most of the standard model, and so we think we know what it is, and we would need to build another accelerator to find if there was other particles that beyond the standard model.
Yeah, question.
Okay, okay, there's a question here.
Yes. Okay, thank you very much, Professor Oppenheim. So I have a question on the two facts of quantum mechanics you shared. The second one, the probabilistic fact. So you mentioned that, I don't know whether it was properties or particles, but you said particles we observe don't have values until they are observed. So I just want to know, does it mean that we discover, okay, so the first one is, what kind of values are you talking about? Like, is it weight of the particles or mass, or like what kind of values? And then secondly, does it mean we discover these values, or do we invent them? Yeah, and then my last question is on the Schrodinger's cat. So I just want to know why cats, what does a cat have? Why did Schrodinger use a cat? Thank you.
Okay, you can take a response to that.
In terms of what are the properties that particles don't have or do have until we measure them, it would be the things we observe about particles are things like where are they, how fast are they going. We often say the momentum. What is their momentum? The things like their charge or their mass, we think those, they have those and they keep those. Those are somehow a little bit different. So those are the properties. And in some sense, even when we observe one of the properties, then the other properties become undetermined. So if we were to measure the particle's position, it would now have a position for a very short time, but then it wouldn't have a velocity. And then if we measured its velocity, it wouldn't have a position. So it's always the case that particles have qualities their qualities don't have definite values. Another example are the quantum bits. So the quantum bits, they are encoded in something, maybe like how it spins, like a gyroscope, and it might be in a superposition of two different ways of spinning, and we don't know what it is until we measure in which direction it's spinning. So there's all kinds of different properties that the particle doesn't have. Why cats? I think Schrodinger hated cats, and I don't know why. But in some sense, the mystery more is that if you have a large object, large objects don't obey the laws of quantum mechanics, or at least we can't see the quantum properties of a large object. And so we don't understand really, we kind of understand why that is to some extent, but what we don't understand is why does the cat, what determines whether the cat is alive or dead and how that process happens. It's something called the measurement problem. Sometimes if you want to look it up, it's called the measurement problem sometimes. There's sometimes an argument about what exactly the measurement problem means, so it's a very contested part of physics.
I'm Kevin. My question was on the fact about the quantum mechanics you're talking about. You made mention about Bell's theorem. But what I know about is that Bell's theorem proved non-locality. So in actual sense, quantum mechanics with superposition try and exploit that theorem that being stated over there. But my question is like, isn't a kind of probability trick that we are dealing when it comes to quantum physics? Because according to Professor Brandes, realize that the only difference between probability and quantum physics is the Markovianity over there. So is it a kind of mathematical probability trick that we are playing in order to explore Bell's theorem over there, or the quantum, to put it in this way, quantum physics kind of seems incomplete in way of trying to describe what is actually happening over here. And another question is, what kind of interpretation do you subscribe to when it comes to quantum mechanics?
Okay, so the first one, if I understood the question, and I think it's a good clarification. So when I talked about this proof that we had that quantum mechanics cannot be described in terms of objective observables, that's true if we want to describe them as local observables. So a particle here, if I want... So there's an assumption about locality which goes into the proof of Bell's theorem, which says that I cannot describe this particle in terms of definite values which occur in this region. And so there's a bit of a, you could imagine some other theory which allows for some kind of non-locality, in some sense some talking between distant locations, that can evade Bell's theorem. And so there is some wiggle room. There are people who try, you know, there are people, people do not like the fact that particles do not have a definite position, and so there's all kinds of attempts to build new laws of physics in which particles do have definite positions. But those all have very unpalatable features which most people don't like. So I would say these are more fringe theories which tend to have such. The question about what my interpretation is, so the one I'm ascribing to at the moment is that, so there are people who have wondered if the fact that gravity plays a role in the measurement problem. And in the theory that myself and my students have proposed, space-time remains classical, matter stays quantum, and it's that interaction between a quantum system and a classical system which causes quantum states to localize with some probability. So that space-time evolves probabilistically, and that's where the probabilities come in. So that's the interpretation that I ascribe to at the moment. My mind can be changed.
Okay, last question.
Thank you very much. I am Atadana. When you mentioned about molecules in our hand, that there is water molecule in our finger, there are also proteins. My question is, take Einstein for example. I guess he was made up of carbon atoms, at least. Is it remotely possible that his carbon atom is in my finger? Is it remotely possible for some reason? If that is remotely possible, or if that is not, probably were his carbon atoms taken away from Earth? The second is, if that's possible, could there be a case that the universe sort of conspires to reassemble his carbon atoms or other atoms of his somewhere?
So the question about Einstein's carbon atoms, it's not just possible that there are some of Einstein's carbon atoms in you. It's actually almost certain that there are some of Einstein's carbon atoms in all of us. You can do a calculation, which are sometimes given in a first-year physics class, where you compute, how much of, say, an Einstein's breath, how is it distributed across the world, and how likely is it that I will be able to inhale one of Einstein's breaths? And that's certain that that happens all the time. So, we live in a world where the number of atoms in our bodies is just huge, and they disperse and mix and are a part of all of us. Whether they could ever be assembled or not has to do with the second law of thermodynamics. And the second law of thermodynamics tells us that once something has spread around the world, it's very difficult to get it back into the box. Just like in a billiard table, if all the marbles are in one little corner and you kick it, it's almost impossible that they will reassemble in that spot again.
Okay. I have the last question.
Uh-oh.
So in your description of the small scale to large scale, I want you to comment about some of your new ideas in trying to describe how one can combine the small scale physics to the large scale physics.
I think that's one of the lessons we learn in physics, that each time we explore a new realm, we find surprises. And I guess that's what's exciting about quantum computing, is we're exploring a realm which we've never explored before. We can perform these quantum measurements, precision measurements, to get precisions we've never had before. And often we know that we will make some discoveries in this regard. And we also know that at different length scales, we get new laws of physics. And so, quantum mechanics is the laws of physics at the very small scale. It seems very unlikely that it will pertain to the physics of the very large scale. I think, though, what's exciting is that there's these, I feel like we're living in an era very similar to very similar to the dawn of quantum mechanics. Because if you think about the history of quantum mechanics, at the very beginning, there was just a few little mysteries, like photoelectric effect, discretization levels of energy levels. There was just a few little puzzles, and then everything unraveled in this amazing series of discoveries. And I feel like we're living in a very similar time, because if you look around us, 95% of the matter in the universe, we only see 5% of it. The rest we think of as dark matter, which we have no idea what it is. We have dark energy, we don't know if that exists or what that is. So the entire universe makes no sense whatsoever. There's all these mysteries like dark energy and dark matter. And then at the quantum level, we have these mysteries like the measurement problem and the fact that things are incompatible with gravity. So it just seems that we are on the verge of a paradigm shift. Of course, you never know when we're at the verge of a paradigm shift, but it feels that we are pushing, we have these mysteries and we are pushing the bounds of what we can measure with, say, these quantum technologies. It feels we're really at the dawn of some kind of revolution in our understanding of physics.
Okay, thank you very much. And we welcome especially you, the young ones, to consider exploring, pushing some of these boundaries so that we are able to solve some of the problems that are being discussed today. Thank you, Jonathan.
Thank you so much. Thank you so much. Very insightful. And we'll go into a panel discussion, but before that, let's come back from the future into the present. Do you agree with me? Yes, because I now understand what the confused faces look like. This is my confused face anyway, but we're going to have a short cultural interlude that will bring us from the future into the present, and then we'll go back into the future when we get to the panel discussion. So ladies and gentlemen, let's put hands together. Let's welcome our cultural troupe to do some very wonderful quantum-inspired performance for us. Please put your hands together for them.
been forgotten for so long. We have been forgotten for so long. Hey, the dreams, oh, the dreams, hey, the dreams that has been forgotten, oh, we have been forgotten for so long, oh, so long. Hey, oh, so long. We have been forgotten for so long. Oh, we have a dream. Oh, the dream. We got a dream. Dreams that have been forgotten. Oh, we had the dreams. Oh, the dreams that have been forgotten. But we still got it. We have it within us. We won't die. We are the stars that will surely rule. We will surely rule. We are that dream that has been forgotten. This is the echo of quantum. Ooh, yeah, yeah. This is the echo of quantum. Yeah, yeah, yeah. We are Ghana. 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 She is not just a gold. Ghana, she's genius. Her children, you, how very beautiful. Cast visions in silicon and circuits. Yes, you. A future is bright. Bright, so bright. But this is not a word play. This is not a poem. This, it is a hackathon. A hackathon of heritage. A love letter. A love letter to the future. To the future. Written in prime numbers. And potential. We will still be what we are. We will still be here. We will still be. We will still be. Oh, oh, oh. We will still be who we are. We will still be who we are.
God is our strength, energy, lives in our hearts, lives in our blood. Seems invisible, but visible. Looks blurred, but bright. You may doubt it, but it exists. It lives in your blood, in your veins. That is the pride of the African. Quantum! The rise of a new world, of a new future. You, all of you, are part of it. Because Ghana is here to bring all of you to embrace the spirit of quantum.
A bigger round of applause for them. This is when creativity meets quantum. A lot of energy in the house. Thank you for that very wonderful, wonderful, wonderful performance. I'm not a scientist, but I have a feeling that when atoms are energized, that is how they behave under the microscope. Don't come for my head, please. All right, so we're moving to the panel discussion, and I'd like to introduce the moderator for the session. She's a very powerful young woman who was named as the world's most interesting mathematician. Yes, she's a Ghanaian, and she is Dr. Angela Tebri. She is the academic manager for the in AIMS Ghana. She works with AIMS Ghana, and she's known for an innovative approach to mathematics and a passion for promoting STEM education. We too will have stars here in Ghana. Ladies and gentlemen, let's welcome Dr. Angela Tebri.
Thank you very much, John, for the warm introduction. What rules govern the science that allow us to take the sharpest pictures with our mobile phones? What about the science behind the warm LED lights we see on this stage? 100 years ago, quantum mechanics was discovered to describe interactions between the smallest units of matter, which Jonathan beautifully described in the lecture. I am Angela Tebri, and I'll be your moderator over the next 35 minutes on the theme, Quantum Technologies for Advancing Global Goals for Sustainable Development. It is indeed an honor to invite world's best experts who have come from very far and here to honor us at this public lecture. I would start by inviting to the stage Karen Halberg from the Balsero Institute and Principal Researcher at the Bariloche Atomic Center. Welcome, Karen. Next, I would invite our Center President, Prince Koriosei, Center President of AIMS Ghana. Shall we give him a warm welcome as he takes the stage? Welcome, Prince. Third, we have the speaker for our public lecture, Jonathan Oppenheim, who is a professor of quantum theory at the Department of Physics and Astronomy at the University College London. Welcome, Jonathan. Final but not the least is Philip Kamalanda, advisor and educator in quantum technologies at the Open Quantum Institute. Can we give a big round of applause as our panelists take the seat? Okay, so let's kickstart. So I would like you to start by giving a short introductions of yourself and tell us about what role you've been playing in quantum in 2 or 3 sentences. I'll start first with Philip. Introduction and what your role in the quantum space has been in 2 to 3 sentences.
Thank you very much, Angela, for the nice introduction. So, my name is Philip Kamelander. I'm working for the Open Quantum Institute, which is an institute based in Geneva that is, has been founded by Gesta, the organization that Stefan has already introduced to us, sharing the main goals of Gesta, which are anticipation and action. And the Open Quantum Institute would like to do so in particular with respect to applications of quantum computing for humanity. And this is what we are working for at OQI.
My name is Jonathan, and I'm at University College London, and I'm a researcher mostly in quantum information theory, quantum communication, and more recently applying it to understand gravity and reconcile it with gravity. And at UCL we also have a quantum master's and have a doctoral training center in quantum technologies, which I am involved in and used to be the director of.
Hi, my name is Prince Osei. I'm the Center President of AIMS Ghana. Also a quantum scientist. My research focuses on quantum gravity and overlaps between quantum gravity and topological quantum computing. I'm also excited about developing young talents in Africa to pursue careers in quantum technology.
Hello everyone, good afternoon. My name is Karen Holberg. I'm a professor of physics from Argentina, from the south of Argentina, Patagonia, a town which is close to Chile. And I do research, and I have students, and my research line is to calculate properties, numerically calculate properties of quantum matter. So it's quantum materials, the properties of electronic structure, electronic behavior, magnetism, superconductivity. So it's basic science, but that's my line of research, and as I said, I also teach physics. My other interest is working towards having raising awareness on the ethics in science and technology, which is very important, and one has to reflect that, also reflect that from professors also with students. What are the consequences of our research? What is integrity in research? And ethics also includes the beneficial applications of our discoveries. So these are my main interests now. Thank you very much for coming.
Thank you so much. I'll go along the last sentence about the benefits of our research. This past week, we have been at the Quantathon, where students have pitched ideas about solutions that will solve some of the SDGs. So my first question to you is, how can we ensure that the development of quantum technologies align with societal priorities rather than driven by commercial and geopolitical interests? How can we ensure that the potential of quantum technology for advancing sustainability does not remain confined to high-income countries, but can be accessible to countries like Ghana or countries in the global south?
Thank you, Angela, for that very important question. We have thought about this, we're working for this, but it also depends on the young generations, and it also depends on all of you. So what I would like to do now is to invite you to reflect together with us on what we are proposing, but it's also mainly it's our responsibility, but together with yours. One of the main problems, as Angela mentioned, is that developed countries, of course, have enormous resources to do research and development. They have a mature technology, so technology that has been working well for many, many decades or centuries, and that allows them to have a quicker and more efficient development of technology and also of science. So how do we keep up with that, or how do we bring all that technology to our countries? Because I'm also speaking from the global south, coming from Argentina. We share many common problems and aspirations. So how do we avoid the opening of this technology gap between the developed countries and the global south? One of the a very important aspect is education, and I think you're doing great, and I want to congratulate Prince, I want to congratulate Ames, I want to congratulate this university and all the educational system of Ghana, because it's my first time in Ghana, and I really learned a lot, and I'm really impressed by the effort and the advances in technology and in education. So we're talking about the first stage, which is education. Then it's important, so before continuing, education has to be done also in collaboration with industry, because it's also important to have not only a theoretical or very basic education, but it's also important to have experience, so a private-public partnership. And the government also plays an important role in stimulating and in achieving these collaborations. So education, this is what you're doing now, but then we can talk about that later if you want. But what are the topics we're going to research, how we do the research, if we're going to use quantum computer that is very difficult for us to build. So can we use a quantum computer in the cloud? Can we go to visit other universities and bring knowledge and come back to our countries to bring back the knowledge? All these things have to be organized and stimulated by government and by other institutions.
Thank you so much, Karen. I'll go on to Prince. Karen, yeah, you mentioned something about a divide, right? So I'll go to Prince. So what is this quantum divide between the global north and the global south? And what is the potential impact that we can do about it, the quantum divide?
Okay, thank you. So there is a significant gap between the countries with huge resources and huge investments in quantum science and technology, and those of us who don't have that kind of resources. And this gap is widening. Currently, there is over 40 billion investments in quantum technology, and this will increase to about over 100 billion by 2040. But it is only currently 0.6% of these investments are in Africa, for example. And for the global south in total, I don't think it's up to 10%. So, and this is concerning because already there's currently a digital divide with about 3 billion people still offline. And technologies like quantum will just accelerate this divide that we already have. So this is what this quantum divide is all about, and we need to address this. And as Karen rightly said, one of the first steps in addressing this is education. And so taking concrete steps and deliberate efforts to educate young people in the global south in these technologies and providing them with opportunities to participate in this development. So that is one. The second thing is global collaboration. So no one country have it all to advance and build quantum computers and develop all the things that Jonathan described in his talk. Across the whole quantum technology supply chain, different resources has to come from different places. And this is where global collaboration is very important. But I want to finish by saying that in the next few years, we know that a third of the young people will come from Africa. And Africa will become the largest workforce, surpassing India and China. And so it is important for us to focus on building, if we are the largest workforce, and technologies like quantum technology technologies of the future that are emerging, then the largest workforce must really be prepared to take jobs of the future technologies.
Thank you so much, Prince. I like your points you raised about global collaboration, and I must add that the Open Quantum Institute is one of our key partners for this whole QTEdu event. And my next question is to Philip. You work with the Open Quantum Institute, an organization that is at the forefront of supporting the development of quantum technologies and its use cases in sustainable development goals. Having listened to this insightful lecture, how can you shed more light on what quantum technologies are and what they can do?
Absolutely, thanks Angela for the question. So quantum technologies cover different fields, and Jonathan has mentioned two of them, which are quantum computing and quantum sensing. So computing for solving computational problems, sensing for accurate or very precise measurements. There are a few other fields like quantum communication for secure communication, or for instance quantum simulation is sometimes distinguished from quantum computing. So there are these roughly four main areas, and the Open Quantum Institute, as you said, which I'm working for, is only focusing on one of these areas, which is quantum computing. Specifically, the Open Quantum Institute is trying to make sure that through our way of anticipating the development in this new technology, everyone will be able to benefit from it, and not just very powerful and rich tech companies, or in particular also the countries that host them. And there are different areas that we tackle at the OQI regarding this. I would like to highlight one, which is connected to your question on what applications can come out of this. What OQI is trying to do is to make sure that the applications that will come out from quantum computing, not today, but maybe in the coming 5 to 10 to 15 years, are also aimed at the benefit of all in terms of helping to achieve the United Nations Sustainable Development Goals. So as an example, this could be a quantum computing solution to make sure that very complex and large pipe systems of water in big cities leak less water. Or it could be in the help of drug development, an application that Jonathan also mentioned in the chemistry simulation area, where quantum computers are used to help understand the effect of drugs and also thereby helping to improve them, for instance, in terms of reducing the adverse drug reaction. And this is what OQI is trying to support through action in terms of us supporting teams that develop such use cases today.
Thank you very much, Philip. So we are making all these advances. We are now in the AI age where there has been a lot of advances, but also there have been a lot of talks about ethics, right? So, and with AI, we made the discoveries before the ethics came. Jonathan, my next question is to you. What ethical challenges must quantum prioritize and today to ensure that it serves as a force for good? And what responsibility do researchers have in ensuring that their research aligns with ethical principles?
I mean, I think one of the issues, we have similar issues with AI, where you have we'll have a few big companies that have these big, powerful systems. The same with quantum computers. It's likely that initially we'll have a few very powerful quantum computers, which are held by a few people. And unfortunately, one of the main applications, or an application of quantum computers, is that it can be used to crack cryptography. So in terms of our privacy, you can imagine that one of the interests that some governments have is to use it to read our emails, etc. I'm not sure that in terms of that, I think it is a lot about protecting ourselves in terms of using cryptography which is resistant against quantum computers. I don't know that we can do anything about the fact that governments will use it to try and do surveillance. So it's about us protecting ourselves and our privacy. Likewise, it's, many of the people in this room are doing things which will ensure that public is educated, that we have a seat at the table, or you have a seat at the table, and are part of the technological progress. I think, otherwise you're just asking people for things, and I think that puts you in a very difficult position when it comes to these large companies. But we have to make these demands.
still in line with the inequities with the big. Yes, my next question is to Karen. So still in line with the inequities of the big companies benefiting a lot, what practical steps, Karen, can policymakers take to prevent quantum technology from becoming another tool of global inequity, and how can we ensure equitable access to quantum technologies?
Thank you. We need teleportation here. Well, this is very important because no country and nobody can do things alone. I think we have to, this quantum technologies is an excellent opportunity to regain collaboration between nations. Now we're facing a situation of increased worldwide insecurity and big technologies like quantum technologies and other technologies, of course, biotechnologies, etc., AI. They have to do with the nation's security, with nation's defense, because quantum technologies and the other technologies also have dual uses. They can also be used not only for good, but also for military purposes, and sometimes not only for defense, but also for purposes that are not that are against humanity or against human rights. And quantum technology is also, it's a very important component of the market. So countries that have, as we already said, a big income or big rich countries can develop the quantum technologies much easier. So how can we do to overcome that? International organizations like the ones we have been mentioning, like GESTA, like we heard today, which has the programs like the OQI, these are very important. And we also heard today from our professor, the internet king of Africa. He was at the ICTP, the International Center for Theoretical Physics in Trieste. I also profited a lot from the ICTP in Trieste because it's a hub where developing countries can go and interact also with other institutions. So not to be long, I think international collaboration is fundamental, the existence of transnational institutions also, and to be able to develop ourselves, we need to have a seat in those institutions and we need to have a say. And to be able to give an opinion on that, we need to be prepared, we need to have knowledge in technology, in this case knowledge in quantum science and technology. So knowledge and education are fundamental to be able to contribute to the world and to our countries in particular.
Thank you very much, Karen. When we think about the investments in quantum, the countries which are having a lot of investments, think of the US, China, and the EU. My next question is to you, Philip. You work with the OQI and just like you deal with diplomacy. So my question is, what is the OQI doing to support policymakers and diplomats in understanding the impacts of quantum technologies?
Yes, I think it's a very good question, and it also very well connects to what Karen just said, in the sense that we have to make sure that the policymakers, in particular the decision makers, are aware of what's coming in this disruptive technology. And OQI is also focusing on making the relevant people aware of the developments that are ongoing through several different ways. So, for instance, OQI is directly speaking with more than 20 representatives from different permanent missions in Geneva, together with also other representatives who are based in their own countries. That's what OQI and GESTA are collectively working on. Another example, which is a very hands-on example, is a so-called quantum diplomacy game. Now that sounds a bit fancy, but what it is essentially nothing more but a role-playing game with which the different players get to know quantum computing, its implications on a technical level to some extent, but in particular on a global level in terms of how do nations and countries talk to one another if a new technology has gets its disruptive power and changes certain aspects of the current system. And this is a very clever way of making people aware. And the OQI, together with GESTA, is promoting this game and playing it all over the world, essentially. So that's another, very active way of doing this.
Thank you very much, Philip. Let's come to Africa and talk about AIMS. Prince, my next question is to you. AIMS is involved in upscaling and capacity building among young and undeserved geographies. What approach should we take in preparing young Africans? You mentioned that in a few years' time, 1 in every 3 young people will be from Africa, and we will form the world's largest workforce. So how are we preparing young Africans for the next quantum revolution to make sure we are well prepared to be able to work in these technologies?
Okay. Thank you. So this is what we've been trying to discuss in the Quantum Technology Education Workshop in the past few days. And there's been a lot of ideas that has been proposed. AIMS is in the right direction, bringing together students from all over Africa and bringing some of the best lecturers from all over the world to come and interact with them. And that's very powerful. I think that the idea of a university and our universities need to be more dynamic and in developing new curricula in response to some of these emerging technologies. We discuss the fact that fundamental concepts that some of it Jonathan has shared here today should be introduced in even at the high school level, because some of these ideas require just basic linear algebra and matrices that can be explained from the point of view of quantum computing at the high school level, for example. And so we have been discussing how even at the undergraduate level, one should introduce possibly a cross-disciplinary minor that covers engineering, computer science, physics, mathematics, and so on, that students could take as a minor with certain core courses and then specialized courses. At the master's level, we have also been discussing having a specialized master's program in quantum technology, but with a specific set of core courses that is broad-based, fundamental, and then having different experts coming from different places to teach specialized program. So I think we have been discussing a lot, and we are organizing a kind of a document that we will share that other academic institutions and universities across the global south can learn from and then be inspired to develop new programs in their different countries to help develop young talents in these areas.
Thank you very much, Prince. The discussion has been very insightful, but we must be aware of time, so we will go around for our final words. To our panelists, I would like to find out from your final words and how on using technologies for sustainable development goals and also for the good of humanity. So Prince, let's start from Karen, then we go down. There'll be time for questions and answers, so you can start thinking about any question you have from the panel. After their final words, we'll come to the audience. Over to you, Karen.
Let's see. I think it's very important to have a very good education and as widely as possible, as Prince was saying. We also have to have a political will. So I think my motto is think globally but act locally. I think this is very important because who else than you know what are the problems of Ghana? Who else than the citizens of Argentina to know what are our problems in Argentina, etc. So it's really important to have a very good education, but then think how to develop our own societies, but always thinking in a global perspective, because after all, we all share one world.
Thank you so much, Karen. Prince, your final words.
I think I will summarize my final words in a quote by Professor Neil Turok, founder of AIMS, that we are analog beings, and we live in a digital world, and we are facing a quantum future. So get ready.
Wow, that's so profound, right? Analog, digital, quantum. Jonathan, your final words?
I can't top that.
Yes, Philip.
I'll not try to top that, but maybe add one more aspect that has not been discussed, in addition to the use case development and the awareness raising with policymakers. It's that we make sure that already in the education that Karen mentioned, everyone on this planet gets access to actual quantum hardware today, and as much as possible. Again, this is very much connected to this monopole that certain tech companies, maybe not today, but at some point may have, just like with the AI revolution, and that's something that we should also keep on our radar.
Thank you so much. Can we give a big round of applause to our panelists? We have time for maximum 3 questions. If you have a question, okay, I see one hand up here. Can we have someone? Yes. Thank you.
Hi, thank you. I have 2 questions. My first question goes to Philip. You mentioned your work has to do with basically having to use quantum solve problems at the UN level, mentioning sustainable development goals, I guess. Yes, so my first question is, which field do you think is very promising right now, where quantum computing can shape or make better? I know most of these solutions we mention is 5 years, 10 years, 15 years in the future. Which area do you think quantum computing is promising that will come sooner? I mean, solutions could come sooner than the other fields. That's the first question. And my second question goes to the education field. I know quantum computing or quantum mechanics is one of the difficult, or let's say challenging fields to get into, right? And here we are with high school students who will be interested in this field, right? I'm someone who is in the field of edtech, where I teach students in several fields like AI, electronics. So wanting to introduce someone to quantum theory, quantum mechanics, I mean, the bar is very high right now. So I want to know if you have any ideas on how we could introduce them without confusing them. I don't know if that makes sense. Yeah, because I have tried myself and I'm still trying.
Okay, I think I take the first question. Thanks a lot for the question. So which fields are very promising for hopefully finding a quantum advantage? To be very honest with you, there is only a handful of known applications today that, once such quantum computers at a large scale exist, will benefit from quantum computers. There is a lot of hope, but there are only very few fields where we know we can prove today that we only need to build the machine and then we will win. And these fields are, one example was mentioned by Jonathan, which is essentially breaking current cryptography. And the other one is computational chemistry / materials development, computational materials development. So this is, in my opinion, the most promising field. It's not the one that will, it may be the one that will benefit first, but then it would mean it would take a long time, because that's not around the corner. That will need us to build the full machine. What happens in between, we can hope, we can guess, but we don't know. So optimization, financial applications that were mentioned before. Today, we can have the hope or quantum machine learning ideas, but we don't know. This is to be decided.
For the education, I think that maybe I hit a little bit hard on some of my colleagues or myself. So the teaching is very important, and I think that from some of the points of view that Jonathan shared, for example, in the beginning, and we've had the chance to teach basics of quantum theory, quantum physics, and quantum computing to high school kids. So it's very simple. It can be explained in a very simple way, and you don't need a lot of complicated mathematics to start. So what we are doing is developing resources that are available online, for example, and also organizing boot camps where we bring young kids and expose them to some of these things. We have the Girls in Mathematical Sciences program, for example, where we have students come to AIMS and we teach them some of these things, and they understand and they do computation. Some of them are here. They participated in the quantum hackathon, and some of them were in the winning team. I'm excited to see them. So it is possible to expose the young people as early as possible. In fact, some argued in the workshop that we can even go below the high school in explaining the basic concept of quantum theory to the young people.
Yes, I agree with you, Prince. I would like to add just one little thing, because these days we were also discussing with Maite Dupois, and she's from the Perimeter Institute. And so the Perimeter Institute is an advanced institute in Canada. And they have excellent material in different languages. Well, of course, they have it in English, but I'm also interested in Spanish or Portuguese for Brazil. And they have many different areas of physics and science, and they have a very good, and it's free, it's open. So you can use it to teach in high school mainly. So these sort of international platforms, I think they're very good. There's very good material out there. Now, I just want to add one thing, that I want to encourage young people to follow scientific or technological careers in addition to quantum. And also, I wanted to say that I'm very pleased to see so many women involved in this Quantathon and in all these activities. And this is very important, because sometimes it's not so easy. We're still struggling to get more women into these careers. And it's a fascinating career, and I will really stimulate you to continue and to have a career in quantum or in general technology and science. So this is what I just wanted to add, sorry.
Our next question.
Yes. Thank you very much. It's been an exciting moment personally for me. Some of us don't come close to science, but our curiosity has brought us here, and I say I'm enjoying this. So I see, yes, the future is very bright with quantum technology. It made me also look back a bit into the past, and I chanced on the development of atomic bombs that is connected to nuclear science, right? And it turns out that actually, so there's a Manhattan Project. If those who know about that history, that's the first development of atomic bomb. And actually, the name connected to it says J. Robert Oppenheimer. So I'm surprised. I don't know how connected it is to you, Professor. But my real question really is, yes, these are great things, wonderful things that are about to happen in the future, and we, gravitating towards it. We see the positives. Can you help us understand, right, the other side of this whole thing, and how people can take advantage of it, like the way atomic bomb was used, right, and see how we can also proactively educate people or water down the potential of the negativities of all these great things that are about to happen. Thank you.
Who would like to take this? Karen, yes.
Yes, this question is really important, and you've touched my heart and my passion with this, because this is why I brought the topic of ethics. This is why it's so important to teach and to talk to our students since they were very young, but also at the high school level, university level, about dual applications and the consequences of our research. When the nuclear energy was discovered, we're talking about 1930s, this was a great discovery, but then it could be applied for nuclear energy, which is good for the SDGs, it's good for humanity, and it was also developed, as you well said, with the Manhattan Project for nuclear bombs. Now we have a great risk that nuclear bombs are used. We have nearly 13,000 nuclear bombs, nuclear warheads in the whole, so pending that they have a capacity of wiping out life on Earth, including, of course, humanity. So what have we done? So what are we going to do, for example, with AI? AI also has potential dual uses. AI is a very good tool, but it can also evolve into something that is better for humanity, that is better for human rights, and it doesn't help our development. So of course I can't tell you a final word on this. The only thing I can say is it's very important. It has to be discussed with students, and it's important for students to realize that we cannot stop technology, but we have to be responsible with the use of technology.
Thank you so much, Karen. Our distinguished speakers will be here during the reception after the closing. And can we give a big round of applause to our panelists as they take their seat? Thank you so much.
Angela, there's one student, senior high school student here who wants to ask a question. She's the only one, yes.
Okay, so a quick
senior
one.
high school,
yes.
yes.
Okay, yes.
So, as beginners, I want to know maybe how we can collectively solve some of the negative effects of quantum technology.
Okay.
Thank you.
Okay, Prince, would you like to take that?
Especially in Africa. We need to continue to advocate, even young people especially, need to continue to advocate for using technologies like quantum and so on for the good of humanity. And so you can do things in your own small way. Some people have good social media. You can read about it, talk about it, that scientific development and advances has to be used for the good of humanity. And let all the young people come together and advocate for this in whichever small way they can. And I think our leaders will listen. Thank you.
Thank you very much. Can we give a big round of applause to our panelists? And thank you. We can all take our seats.
Let's put hands together for them. Wonderful discussion. A bigger round of applause for ourselves. Very interesting questions. And I'm sure you've really learned a lot of things that will go a long way to help humanity as a whole. Big round of applause for yourself. Thank you so much. At this juncture, we'll take our concluding thoughts from the president of AIMS Ghana and the director for Quantum Leap Africa, Dr. Prince Osei.
Okay, I just want to say a big thank you to all for your attention and for coming. And I want to acknowledge all our partners and our supporters at AIMS. The Open Quantum Institute has been a very amazing partner for us for the events this week, and Jester as well. So thank you very much. Please, let's give a big hand for our partners. We have other partners who have supported us throughout the programs. We have the MasterCard Foundation Scholars Program that's partnered with the Quantum Hackathon, and they have been very amazing supporting AIMS, providing scholarships for our students. We also had NYU Abu Dhabi Hackathon supporting our students. Google, IBM, Quantum Delta NL, a lot of amazing partners who supported us. The Ministry of Education, the Ministry of Science and Technology, Ghana Academy of Arts and Sciences. A big thank you to you all, and thank you very much for attending. Thank you.
All right. Thank you, sir, for thanking all of us. Can we put hands together for the Center President for AIMS Ghana? So before we leave, we would like to capture this moment in history, and we would ask that we'll all come upstage. Our speakers and our special invited guests will line up in front of us, and then we'll take one picture or two or three, and then we can keep that in our archives as well. So if you don't mind, please join us. But before you do that, please know that there's refreshment for everybody here. So once we are done with the pictures and engaging and networking, let's use this route upstairs. there's a place where you'll be given a designated takeaway, which contains our refreshment for today. Right. I think there's something about not bringing food in here. I don't know how we can go about it. Yeah, but that's the warning we have received. But please, there's a lot of refreshment for all of us. When we finish with the pictures and then you engage a network, we can just use the stairs, climb up there. Our ushers are lined up, ready to give us our refreshments for tonight. So ladies and gentlemen, well done to ourselves. Please, let's move upstage. Our special invited guests, our guest speakers, our partners will line up in front, and then thank you once again for coming. Thank you. So yes, the rest of us will move up the stage. The chairs will be moved back so that we can have enough space. So please, let's head towards the stage at this point, and let's all be part of the photograph. Yes, please come close. Let's get up the stage.
Baby, let me take a look. Oh Lord, me want all the girls in the whole world. I know what I'm doing is so wrong, but since no man can focus, we definitely don't give a. She said she know me got a girlfriend, and so what? What if I do? She said